All right, thanks for having me. Today I will be talking a little bit about Kubernetes Cluster Autoscalers and specifically how you can virtually plug any cloud provider into using it. So a little bit about myself. I am a software/infrastructure engineer here at Vision. I focus mainly on building Kubernetes platforms, different kind of tooling, and making sure that my colleagues don't get paged at 3 a.m. trying to. In my free time, I have my own blog website where I also write about different infrastructure, Linux, Kubernetes related topics. And when I'm not behind a computer, I'm usually somewhere hiking, combining that with photography, and or also playing guitar. All right, this is what I would like to talk about. So first off, I'm gonna take a bit of a step back and look at how the cluster autoscaler actually works, how I used a special cloud provider plugin called external gRPC, and how the SIG autoscaler thinks about the future of the entire project. I will go a bit into how I actually build it, what it takes to do that. There's going to be a live demo, and at the end, some gotchas, takeaways, and of course, questions if there are any. All right, let's get into it. So the autoscaler, the core component, it knows when, but not how to scale. So mainly what it does is it knows when to scale up according to if there are any pending pods on a cluster, or the opposite, when to scale the cluster down, depending on nodes that have been idle for a certain amount of time. How it creates the VMs and how they join the cluster, that is out of scope. It doesn't know about that. For that, Cluster Autoscaler requires cloud providers, which if you've used the Cluster Autoscaler, you know that there are a lot of bigger clouds in tree, which you can already use, but the smaller ones, smaller clouds may be a bit left behind there. So how does it actually decide when to scale? Since we are in Kubernetes land, everything is a controller. There is the pattern. So if you don't specifically configure anything, it has this reconciliation loop every 10 seconds where it goes through a few things which it asks itself. Like, for example, are there any unscheduled pods which are in the pending state? Would they fit on a node group which has been defined by the user? So this is like a scheduling simulation which it does. If so, it sends it off. It invokes the cloud provider to say, increase the size of the node pool, where it sends the delta, how many more nodes do I need. The same goes, as mentioned before, for the other side, the other way around. If something like a cluster is has been idle, some nodes have been idle, it can detect that and do the opposite, delete nodes. So let's zoom in maybe a little bit more. So how the CA actually picks a group, if you have multiple node groups defined. There are many components involved, one of which is the estimator. This is the most important one. So what it does is it goes through a simulation of all of these pending pods. How many nodes would I need to accommodate all of these? Then next up is going to be the expander. So, okay, what if the user defined multiple node groups? Which one should I pick? There's different modes you can choose. As you can see here, by default, it's going to be random, which is interesting. Then it also has a way of tracking upcoming nodes when it decided, okay, I need this one. It has the ability to mark that so it doesn't create even more in-flight requests. It does account for daemon sets. As we know, they like if you don't define anything special, they get scheduled on every node. So it does accommodate for those requests. And there's also a backoff mechanism. So at this point, the cloud provider doesn't know any of this. Based on these decisions, that will be handed off when calling the increase size function. So let's go a bit back to the simulation, which I talked about. In this case, I call it like the simulator is the scheduler, because to some degree, the cluster autoscaler imports the actual scheduling framework of Kubernetes to go through all of these filters and predicates it needs to score these conditions. So there are like a few, as you can see here, like which can score like affinities, tolerations, and all that stuff, which we all know. It can do those simulations as well. And the way it does it is by creating a snapshot of the live cluster, what's there. It does it in a way that it copies it into memory and runs those simulation against the in-memory copy, which is quite cheap. So it doesn't have to like always fetch the entire cluster, because imagine if you have a large cluster with hundreds of nodes, that's going to take a while. It does that by the copy and write methods, where it underlying uses like fork and revert, so it can easily switch between those simulations. So what do you do if your cloud is not on the list? So in my example here, I had a case where I needed autoscaling on a cloud provider called CloudScale, and went into the cluster autoscaler repo, checked what there is, like in the in-tree, of course, wasn't happy, there was nothing, was a bit bummed about it. Then I asked myself, okay, what should I do? And realistically, there are three options you can do. Either you try to get your PR merged into the upstream repository. That means you invoke all the release cycles, you invoke all of the complexity, and if something changes for anything else, you also have to be ready to change your stuff. The other thing would have been to fork the autoscaler and essentially keep a copy of that and keep track with it myself. Or the last option would be external gRPC. This is one of the many cloud providers which they have in there, which is a way of plugging your own program basically, which can have all of this logic but just sent off to your external service. All right, so while looking into this stuff, I've actually seen that, I've seen a maintainer talk by the SIG Autoscaler group, which talked exactly about this stuff. And essentially, they know that this is not like very maintainable or a good process of getting your provider in there. So there is a proposal going around addressing all of these things. So what they're trying to do is go a bit more in the direction which, for example, Project Carpenter uses. So where they have like the main repository where all the logic lives, you can use it as a library, and you maintain your own repository specifically for your cloud provider integration. This is still going on. There is no consensus on this, but it is a direction they want to steer in, from what I've seen and understood. Interesting to say, though, it's the intention behind it is to like split everything out, keep just the test providers they have in there, and also keep the external gRPC as a first-class citizen provider in there. So, which leads me why I went with external gRPC in the end. So after reading this, I thought, okay, that is the way to do it if you're just a random guy on the internet who wants autoscaling on CloudScale. Which this allows me to not be confined to all of these rules they have upstream. I can have my own release cycle for it. I don't have to, just go into all of that. Also, a very cool thing about it is, since it is a gRPC service which you are implementing, you could write it in any language. So I chose to go with Go because that's my main language I use these days, and it is also proven to be future-proof. And if they change it, they do the split, I can still adapt to those changes, but I don't have to. All right, so now that we know why I chose it and what it is, this is like a very high-level overview of how it is configured. So you have on the left side the core logic, the cluster autoscaler, which I would say is like kind of the brain, which it decides how to do things. And then over MTLS connection gRPC, we have the autoscaler CloudScale, which is provided by me, which is the hands. It does the dirty work on CloudScale. So this means you would still define the different node groups which you need. And in this scenario, the cluster autoscaler can then, if you have like an actuator, let's say like a deployment or an HPA or something, it can schedule it. There are pending pods. It picks it up, goes through this entire scheduling simulation, hands it off to the autoscaler CloudScale, creates the VM according to a blueprint, and it joins the cluster. And then the actual scheduling simulation by Kubernetes run through, and they schedule it on the actual new nodes. So to do this, it's actually quite, it's a lot easier than I thought initially. So there's this gRPC proto file which you can get, which has a bunch of RPCs in there. But you don't have to actually implement all of the RPCs from that service. So mainly you need just these few, like 6 methods, which basically do exactly what it was portrayed in the architecture overview. So it knows how to refresh, how to reconcile with the actual CloudScale VMs, what is there, what do I have in state. It knows about all the different node groups which I have defined. It can map an actual node to that group, so it knows where it belongs to. Then it has also like a template node info, which is used to do simulations. I will come back to that a bit later. And then of course like the methods to say, okay, how do I create a new server? How do I delete it again from CloudScale? I will go a little bit into how this works. So this is very easy, like a refresh. What I do here is basically when I create a new cluster, I tag them with a special tag which is defined in the node group, and via that tag I can go list them and just build my my difference according to that, and know how fresh is it and is there something off. So this is where it gets a little bit interesting. So when you have a fresh cluster which has no nodes yet, so you basically end up with just a control plane node, let's say, and you schedule some workload on there. So how does the simulator know what to simulate? So it doesn't know what nodes exist yet. So here's where the template node info comes in. This is essentially just a V1 node type, which you tell the autoscaler, hey, this is how a node would look like. You know, like how many CPUs, how many gigabytes of RAM, what kind of disks, any special devices, all of that stuff. And if there are 0, it takes that into account and runs simulation against that one. The other job of the template node info is to avoid creating too many nodes. So I've told you that it runs every 10 seconds during, let's say if something takes a bit longer, and during those 10 seconds it detects again, oh no, I have to go off and create even more nodes. It counteracts that problem by just annotating it with the upcoming node annotation, so it knows, hey, I was already scoring this. This is going to happen, but I'm not there yet. Exactly. So these are the two jobs of the template node info. So which means you kind of have to lie to the autoscaler. So this is what I was talking about. You have like the V1 node. This is a very condensed version of it. But what it does is basically taking like from the flavors list from CloudScale, depending on what I defined in the node group, it can like create such a V1 node and send it off and do simulation against. What is also special and often forgotten about, I've seen, is that when you create a node, you don't have like all of the capacity which you give it in, for example, here in resource vCPU. So since the system reserves a chunk of the resources itself for prioritized stuff like the Kube API server or whatnot, like anything else. So what I do is I do subtract those values from what I create in the V1 node to, you know, create a little bit of a more accurate template of a node, which is still a bit hard, but it's better than not setting anything. So which leads me to a few problems which I run into when building this actually. So I had this all mapped out, tried it, nothing was happening. And one reason for that was that I set the resource pods of a node, well, I didn't set it at all, which defaulted to being 0. So it basically tells me, yeah, this is a node, but I don't accept any pods. Nothing happened. Yeah, oopsie. And then the other thing was that was just on me, again, for not reading the upstream source code good enough. I sent basically the results of that in a wrong format. So learned that the hard way. All right. So also very interesting thing. You might be asking yourselves, okay, like things can go wrong when you create a new server. What happens? What does it do? So basically, when I detect that there is a delta of VMs which I have to create, I do increase the target size. Like it knows internally, this is the size I'm aiming to have in a locked fashion, so it doesn't create any races. Sends it off. If nothing happens, like let's say it doesn't boot or it failed for any reason, it has this special node provision duration time, which is by default set to 15 minutes. So this is like a kind of a guardrail to say, okay, if nothing happened in 15 minutes, this node, which I should have joined, didn't join, it can remove it again. So. And this also brings me back to the tagging of nodes. This is very important that when you create those nodes, you will have to tag them, otherwise it will never know which node is this, because maybe you have other nodes in your same cloud scale subscription. All right, this was a lot of like the when and how to create it. So how it basically joins, like let's say we created the VM, how does it actually join the cluster? In my scenario, that was through feeding it the user data. So I use Talos Linux for building my Kubernetes clusters, which I created a machine config. I fed that to the node group config on my cluster autoscaler. It takes that, creates the cluster, passes through the user data, and through that machine config, it knows, it has like all the certificates and the join tokens, and it knows how to join it. What is an absolute hard requirement is that it has a CCM, which can actually stamp those nodes with a provider ID. That is used to actually get the ID, so it can map it back and check on those. All right. Yeah, and that it does that by this special RPC. Exactly, it extracts it and it goes through like, hey, does this belong to me? This is what is on cloud scale, and so on. All right. So to recap, to build your own autoscaler for any cloud, you would have to take the external gRPC service, implement at least those 6 very important RPCs. There are, of course, more, but you can just implement them as unimplemented, which there is. Pick a tag, how you want to tag your nodes in the actual cloud scale subscription. Make sure you have a CCM. Decide on how to create your machine config, which you need to feed, and try to get the template node info mostly right. All right, so this is basically me, but you don't see it, but internally that's me. I'm gonna try to demonstrate this. Let's see. I think that should be good enough, and if not, you have to squint a bit, I'm sorry. Okay, so on the upper left side, that's actually like the configuration of the autoscaler. And here, the most important bit is this whole node groups block, where I tell it like, okay, use this custom image. In my case, that's a Talos image. The flavor is going to be a flex 4.1, how to label it, very important, the range, like I tell it like, okay, I want my node to be scaled between 3 and 0 nodes. A lot of like some networking stuff, how many, how big should my node's disk be, and all that stuff. Then let's see. As you can see, I have right now on cloud scale just a single node acting as a control plane running. So it doesn't have any workers. So to simulate this, I have on the right side here a very stupid deployment, very stupid. It has 50 replicas. It just starts the pause pod, which you know does nothing, it pauses. And of course, it has some requests set. Now, let's see. Right, there it is. CPU for 500 and a little bit of memory. So we can now just try to, apply it. that's applied. And we can try to watch the state here. So we might not see anything yet, but maybe, yeah, look at that. We have, like, on the actual Cloud Scale dashboard, we can see it is already spinning up a few clusters. Maybe we can even go into and check what it does on the dashboard, on the console. There we go. It is booting. It found the right image. I'm going to fast track it a little bit. So now what happened is it found the right configuration and it's installing it to disk, and now it does a whole reboot cycle again. And now should be soon. Oh, there we go. On the right side, we can actually see there is stuff happening. They're still not ready, but they're coming up. And we can actually see on the upper left side in the cluster, that's like the overall state. It found all of these 3 new machines, that it has now 4 machines in total, including the control plane, of course. Yeah, and they're ready. And now on this side, there should be at least some of the pods. Oops. Yeah, so at least some of them were got scheduled, of course. Those are very, very small nodes, so that's why I cannot accommodate 50 of them. Yeah, and basically what this showed is like the whole scheduling simulation. So I had no nodes in the cluster, so I'd used the template node info to run the simulations, joined the cluster, scheduled them, and that's it. All right. Yeah, that basically concludes my my talk. Here are some links if you want to check it out. There's the code. Please feel free to check it out. Ask me a lot of things if you have any questions there. There's my blog post, and also I've included like those issues from the SIG autoscaling group where you can track where this is steering. All right. Do you have any questions?